Okay, so let us go with general thermal analysis of convection heat transfer. So these all these things are done. So let us go with general thermal analysis. General thermal analysis. General thermal analysis. Let us see. Generally, what we know is, okay. So if you take a pipe, there are two things which is very important. One is Q dot is what? Q dot at any place. Okay, so you can write it as MCP. What is flow going through the tube? It's a bit difficult, students, to understand. Okay, so you have to put a bit of efforts here. So this would be TI. This would be T naught or exit. Let us put TE. What are TE and T naught? TE are T naught and mean temperature at the inlet and the exit. Okay, so Q dot, the heat transfer which is happening through this side, which is Q dot, can be written as Q dot. In the sense, I'll write small q. Wait a minute. So let me dot. Okay, let me dot Q dot because heat flux Q. The Q dot is equal to, I can say, or wait a minute, MCP. No, no, no. It's Q dot only, capital Q. I'm very sorry. Don't write. It is MCP, M dot CP into T exit minus T initial. Correct. That would be the total heat transfer, is it not? So what heat is going in here is M dot CP T I, and what is going out here is M dot CP T E. Make sense? The difference is going through the walls, is it not? Yes or no? Okay. So now, or generally, we can also say that if I say it has a, yeah, so the surface can be done in two ways. Okay, now here we can say from here to here, the wall temperature which is there is changing. So there is a variation, is it? Or there might be a variation. Okay, so there are two conditions which can happen, and another point with that. Okay, another point which can happen is at any section, at any section, at any section, the heat leaving the surface, leaving the fluid, at any section, the heat leaving the fluid to the walls, to the walls can be Q dot is equal to H at a particular X. H is the heat transfer coefficient at that particular place at any section. Okay, at any section into T wall or T mean minus T surface. If it is hot, is it not? T mean minus T surface. Yes or no? So with this, there are two conditions which is there. So this is at a particular X. Now T mean will vary, is it not? T mean can vary. Correct? T mean can vary from one place to the other. So here TE and TI are mean temperatures, mean temperatures at exit and inlet. Correct? In this, there are two conditions which can happen. Okay, two THX. Sir, T wall. Sorry, T wall. Fine. I'm copying from our Senjal. Senjal uses TS. I want to use T wall consistently. Okay. So now here, one of the points which is there here. See, I'm referring to Senjal, but I'm not copying from Senjal everything. Okay. So I'm just this is a subject in which I have such a hold that I can say I can just see Senjal and see what I want to say. But one reference is required. So Senjal and Nag, these are the two references I use. But not always I copy everything what is given in Senjal. Okay. So here, although I do copy sometimes, okay, I have to refer that. Okay. So Hx is equal to Tm minus Tw. Is it not? Or Q dot is equal to Hx into Tm minus Tw. Correct. Now there are two conditions. There are two types of there are two types of cases or simplifications that can be considered that can be considered. First one, first one, heat transfer, heat transfer with constant heat flux at the surface throughout the duct. Constant heat flux throughout the duct. First thing. Second one, heat transfer. Second case is heat transfer. Heat transfer with constant wall temperature throughout the duct. Constant heat flux is there in some cases, constant surface temperatures are. Some cases both are there together. You cannot say that. You cannot get into this. These are some of the extreme cases which can happen. Not extreme in the sense, they can happen actually. It depends on what you want to see, how you want to see the problem as. And this is the basis of our heat exchanger design. So I'll take a bit more on this so that heat exchangers will become easier. Okay. He's saying please upload heat transfer. So bad I am. This person constantly sees it. Pencil. He's not attending heat transfer classes. One second, I will add it now itself. Okay, because sometimes I have to. One second. Just a second. I don't want to disappoint him. I feel bad because he will lose his. What you say? See, interest is important, is it not? So, one second. Just upload it. Okay. Just a minute. I'm seeing it now. Sure. Okay. Now, what to you, students? Okay. Sure. Yeah. Please write. Pragyan Patnaik is hiring radio frequency analyst designer. Yes, struggled like anything. It's Pragyan Patnaik. Avrati Technologies Private Limited, Chennai. Incubated inside this. When I'm seeing him from 2010 in IIT campus. Doing big things. Success he did not get till now, but he's getting stipend at least to start a company. He's getting a lot of Chai, different person. We sat and talked a lot. Then all the people, even Suresh was like that only. We talked a lot in our canteen. A lot of times we sit, we talk these ideas only. So the good things will happen when you talk. When you talk, and don't think nothing is what you say. Nothing is no ideas are stupid. No ideas are stupid. Okay, you have to implement it. That's it. When you implement it, it becomes fantastic. Okay, and for implementation, you need to have that wherewithal. First of all, you need money. Okay, to sustain yourself, and that money is given by government of India. You don't have to struggle. To test something, you need to money that you can get from the people who invest. Okay, you can get it. You don't have to pay from your father's money. No, no, not at all. So that is the beauty, is it not? So, fine. Anyway, so now here let us see first one, which is constant heat flux. Constant heat flux. So let us take constant heat flux, which is Q dot S. Q dot wall. Q wall is equal to constant. Okay, this is what we will see. So what's going to happen here is Q dot, which is equal to Q dot S into AS would be equal to M dot Cp into T exit minus T inlet, the mean temperatures. So what is going to happen is if you have a pipe, okay, say there is T I which is going inside and TE which is going outside, okay, temperatures. Now plot, if I plot the L, that is X, this side I will say X, okay, versus if I say temperature, mean temperature. So this is T mean. So I'm going up with T mean, okay, T mean temperature, right? So now what happens initially, you will have this mean temperature generally goes from constant TE, TI to TE, mean temperature. We have to keep constant heat flux. So if this is a hot fluid, okay, sorry, if it is a, if I consider to maintain the same heat transfer coefficient, what should I do? Suppose I have entrance region, so if you have to maintain constant heat flux, then what you should write? Heat transfer coefficient is more here. So I have to maintain wall temperature in such a way that the difference here is the same. So it will go here. Okay. This is what T of the wall. Why I'm keeping this T wall lower here? I'm keeping the T wall lower because heat transfer coefficient is more in the developing region. So what is this? This region is developing. This is developing region. This is developing region. Make sense? So for the heat transfer, because Q is what? Q is equal to H into delta T. In the entrance region, Q is H is higher. So when H is higher, delta T should be less, is it not? What is this distance? This distance is delta T. Make sense? Which is equal to T wall minus T mean. Make sense? This is the T mean which is going. I'll write this is T. No, instead of T mean, I'll write this is T. Temperature. This is the T wall. This is the T mean variation. T mean varies from Ti at the inlet to Te at the exit. Make sense? T mean varies from Ti at the inlet to Te at the exit. And this is the variation of T mean. This is the variation. The top one, the top curve is the variation of wall temperature. The bottom one is the variation in the mean temperature. This is of the fluid, this is of the wall. And there is a heat transfer between the wall, a fluid to the wall. There is heat transfer from the fluid to the wall. No, we are saying if we have to keep the constant heat flux, then we have to change the wall temperature according to the changes in the mean temperatures. If you want to heat flux, this is what this is a cold fluid which is now this is what is this? This is a cold fluid which is heated up. You have to think in both the ways. In some other graph, it might be something like this. Now, hot surface. It might be a boiler. Increase the wall temperature accordingly to keep them constant heat flux. This is sometimes used in our boilers. You see, in boilers, if you see, the hot flue gases will go to the superheated region. The other things, the leftover flue gases is used to heat the cold fluid to give the sensible heat. To give the superheat, you give hot fluids, hot flue gases. Make sense? Good. So if it is a constant heat flux, not that it there everywhere constant heat flux is there, but if we have to maintain constant heat flux, then this is how we have to go. Temperature has to change as the mean temperature changes. Make sense? Fine. Okay. Take some time, take time to understand this. Because heat flux H is same. After developing region, H is same. Tm has to, delta T has to remain constant. So wall temperature has to increase by some means. You might be doing electrical heating or anything. Electrical heating is more controllable. Right? You can have control systems later on to control the heat. That's what is done in our chemical engineering plants. You go to MCF, MRPL, you have to heat. So that control is very important. Even in boilers, they use a lot of controls. They are using differential equations. You do not know. You will see big what do you say, boilers. It says, sir, there it's great. But it is differential equation in action there. Correct? Okay. Sure. Further going. Now here, since Q is equal to Q wall dot is equal to H into T wall or T wall minus T mean. Correct? T wall minus T mean. You can write T wall is equal to T mean plus Q dot wall by H. It can be plus or minus. It need not be plus only, it can be minus also. Depends on the direction in which the heat is flowing. Make sense? So that adjustment you have to do. Okay. So now further going, we know that, observe here. Okay. See here. If I say, in case you write this down, this is not done, then I go with the next slide. Very important this topic is. Right? It needly spend time to understand those. If it takes time, I'll take extra classes.
But in reality, can we keep it? Can we do something?
Control systems, if we have, we can do it. Why not? Electrical heating, we can do it. You know. Even boilers also, we can do it. We can do it. No problem. Controlled heating has to be done. Done. But with plus or minus, there's tolerance always. You can minimize the tolerance. That's and think case, extreme cases. You're taking a case where you want to continuously increase the temperature. How do you increase the temperature? You're heating. Simple. So generally, what happens in heat exchangers? This is used. So if you want to heat, say, your see, there is one tube here, and there's another thing which is going. So what happens? The cold fluid goes to the place where this is exiting. It's actually counterflow heat exchangers. This kind of things happens generally in the counterflow heat exchangers, where the cold fluid is entering the heat exchanger like this. This is a cold fluid, okay, and the hot fluid comes like this. I'll say this is the hot fluid. This is a tube which has hot fluid. Ah, in different dimensions. This is hot fluid, and this is cold. Getting the point? Or you may have cold, hot, yeah, hot fluid, or sorry, cold fluid, and outside in the periphery you have hot fluid. So that heat flux is constant, is it not? This is the extreme, or you can say it's normal, right?
What what do we achieve by keeping the what purpose does it serve? Constant.
Um, no, no. The thing is that this is what happens in counterflow heat exchangers. In counterflow heat exchangers,
It is like
hot
it absorbs equal to heat.
heat rejected, yes. Heat absorbed by the heat rejected by the hot fluid is equal to heat absorbed by the cold fluid. Now, if you put it here, then cold fluid is heated a lot. Hot fluid, as it goes, it cools down. This heats up. Then what? You can have a particular type of thing only. See, for example, if you have a cold fluid, now here cold fluid is at a low temperature. Hot fluid is the high temperature. So what will happen? Cold fluid will go like this. Hot fluid will go like this. It will reach this temperature only. The heat transfer is reduced. Now, in case it is cold fluid here, sorry, cold fluid is increasing the temperature. In the second case, what happens? It comes from here. Hot fluid is decreasing the temperature. This is the entry. This is the say inlet. This is the exit. This is the inlet. This is the exit. This is hot fluid. This is cold fluid. Make sense?
Then you get the constant heat flux affecting the
Hmm?
affecting the maximum temperature.
We will see that later. We'll see that later.
So it's more of ideal.
We'll see that later. All the other things. Now I'm telling you where is the case. That's what I'm telling you. So the temperature difference is almost the same. So the heat flux remains same. There are more to this, but I'm telling you for see. Sometimes you need to think. Is it not? You have to think. You need to think. That's why I'm giving examples. There are various other examples also. This is what I could think now. So I came up with this.
Sir,
Makes sense. Sure. Next.
that
Yes, please.
ಕೆಳಗೆ ನೀವು ಡ್ರಾ ಮಾಡಿದ ಅದು ಕೌಂಟರ್ ಫುಲ್ ಆಗ್ತದಲ್ಲ ಕೆಳಗಡೆ ಡ್ರಾ
ಯಾವುದು
ಮಾಡಿದ್ದೆ ನೀವು ಅದು ಕೌಂಟರ್ ಫುಲ್ ಆಗ್ತದಲ್ಲ
counter counter flow heat exchanger. Sorry, yeah. Next, that is just for explanation. So now what happens? Let me take a part of the heat exchanger, a part of the tube where you have say this is going in with m dot cp t mean, and this is going out with m dot cp t mean plus change in t mean. And then here, if I say it's increasing, so I'll say the heat is transferring inside, which is dq dot is equal to h into t wall minus t mean. Correct? I can have it like that. Into actually dA is the surface temperature. That is it. So you can write dq is equal to h into T wall minus T mean into surface temperature dA. It's not the cross section, it is a surface temperature. Or area of the wall, I can say, AW. And here this, I will write it as dx. Right? So if I do that, what I'll get? M dot Cp into dTm. This is the heat which is increased, is it not? dTm can be equal to, from the figure, referring to the figure, I can have Cp dTm is actually equal to Q dot on the wall, into, if you consider here, it is perimeter into dx. P is the perimeter. I'll write P capital because small p we are using for pressure, where P is the perimeter, of the duct, because this gives the area, is it not? Area is area of the wall, AW is what? Perimeter into the dx, is it not? Sure. Now, that means I can write dTm by dx is actually equal to, this is very much used in heat exchanger design, okay? dTm by dx is equal to q dot wall, into perimeter divided by m dot Cp. Agreed? Yes or no? So this is a very important equation. Write this down. Number, I don't know. What was the number? Did we follow the number? Yes, we followed some number, but then we lost in a minute. Is it not? Oh, one only we gave. Okay. It has a lot of things. Just leave it. Okay, we'll not number it at all. Let us write this. You can number accordingly whatever you want. Okay? Now, now, since 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 q dot wall and h are both constants, are both constants, both constants, since these are both constants, okay, differentiating, both constant differentiating, I will put the numbers here, okay. Let me put this as A, let me put this as B, let me put this as C. That means afterwards when we go, we are dropping this C, and let this be D, a constant. Okay. Now since Q dot and H are both constant, okay, differentiation of differentiation of equation, differentiation of equation B, equation B yields dTm by dx is equal to dt wall by dx. Correct. Correct. And what is dtm by dx? Q dot p by m dot cp. Right. This is very important. The equation is very, very important. VV in. What is meant by in? IMP in, short fellow. Does imp mean short fellow? It's all because of Lord of the Rings. No, Lord of the Rings. Game of Thrones. In that it was a small imp, is it? Who helped Daenerys. Come on. See, you've seen a lot of Lord of Thrones, Game of Thrones. No, don't see. It's addictive. Huh?
It's addictive and disappointing.
Yeah, yeah, that's true. Disappointing. Because at the end, everything is. Yeah.
But don't spoil it for them. It's fine.
Huh?
Don't spoil it for them. If they're watching at some point, later let them watch.
Let them see.
So
Yeah,
they
yeah, yeah,
can
yeah.
join the club.
Yeah, let them ruin themselves.
Expectation.
Yes, 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 yes. Chalo. So dtm by dx is equal to dtw by dx, right? So now next one. Now this implies it's not Indian cinema that it keeps everything nice. Okay. See here. That means dou t by dou x is equal to dt wall by dx is equal to dtm by dx is equal to q dot w p by m dot cp is equal to constant. Now the question what comes here is, sir, how did you say dou t by dou x here? This is fine. We are clear with that. Okay. How come dou t by dou x? See, dou t by dou x is equal to dtw by dx because the non-dimensional temperature, the dimensionless temperature, temperature T wall minus T divided by Ts minus Tm is equal to Z is equal to constant is equal to constant in a fully developed flow. Write it along with me, students. You have 5 minutes. That is coming now. Fully developed flow. W T W. This is T W. S not S. T W. T W minus T divided by D W by dx. Right. Is constant in a fully developed flow. Correct. So now what happens when you differentiate? You get this implies that dou t by dou x, dou t by dou x is equal to dt or dou t wall by dou x, which in fact dou t wall changes only with x. So this can be written as which is equal to dt wall by dx. Makes sense? Now, thus, in a fully developed flow, thus, this is important. So this is important. Thus, in a fully developed flow, thus in a fully developed flow, in a tube, in a tube subjected to constant surface heat flux, to constant surface heat flux, constant surface heat flux. The the temperature gradient is independent of x, and thus the shape of the temperature profile does not change does not change along the tube. Very, very important distance. Shape of the temperature profile does not change. Although the quantity may increase, shape is the same. You may get here, you may get like this. Next one, it may be like this, and then this. I'm exaggerating. This is the same thing here. This is yes. You understand? The same. I'm copying this part and pasting it. If it is increased, if it is decreased, go from here to here. Shape is not changed. It is like in AutoCAD, you have stretch function. You hold something here and stretch it. In during the AutoCAD, in AutoCAD, there's a stretch function, not extrusion, stretch. 2D. This is 2D. Crafting. You have that, stretch function. Yeah. I taught around 60 batches, 60 batches. I used to count. Now I forgot the count. More than 60 because morning to evening I used to take AutoCAD for around say 1 year. AutoCAD continuously. In a day I used to take 8 hours of classes there also. Fantastic. Then the habit happened of taking more classes. It was like this one, in front of the computer and being projected. Okay, students, thank you very much. Okay, we'll meet at 7:10.